Now we have derived the expression that is 1 by lambda is equal to PO2 by PO1, where lambda is the operating pressure ratio for this convergent divergent nozzle when the shock wave is just standing at the exit. Now what happens that when we attach a diffuser, a normal diffuser at the exit of the convergent divergent nozzle, where normal shock is just standing at the exit. In this case, since the flow across it, then let us say if that pressure, stagnation pressure, is PO2 dash, when PO2 whereas by attaching a normal or a plain diffuser at the exit of the convergent divergent nozzle, let us say at the exit point we obtain PO2 dash, which is further lesser than PO2. That means PO2, which is further more than the PO2. That means whatever the stagnation pressure loss was incurred across the normal shock wave is recovered back, and the pressure increases to PO2 dash because it meets the flow, subsonic flow meets a diffuser, and hence the flow decelerates and the pressure, total pressure, rises. In such case, if that becomes PO2 dash, then likewise we derive the early expression, we replace PO2 with PO2 dash, and we can write down the expression something like that: PO2 dash by PO1, and hence the Mach number change from M1 to M1 dash, and likewise here M1 to M1 dash here. In this expression, please note that M1 dash is the Mach number of that shock location, because as soon as you attach a diffuser here, this shock wave which is standing here moves to the diffuser somewhere at this location. So M1 dash is just at this location Mach number across which this expression is written, and hence this lambda dash will become the particular operating pressure ratio for running this convergent divergent nozzle and diffuser assembly for this particular case. And what we essentially see here, that the lambda dash, the operating pressure ratio required to run this convergent divergent nozzle and diffuser assembly, will be lesser than the actual one. That means the operating pressure ratio requirement decreases. That means it is fuel efficiency point of view, you have optimized the pressure ratio, and or a lower operating pressure ratio is required to run the nozzle, convergent divergent nozzle, when a normal or plain diffuser is attached at the exit of the nozzle. And this kind of geometrical configuration such that the standing wave at the exit of the nozzle moves to the diffuser side, the plain diffuser section, is termed as normal shock recovery. Now instead of attaching a plain diffuser, if we have the another configuration called convergent divergent diffuser, which is shown here, the geometry is similar to a convergent divergent nozzle, and this kind of profile is termed as CD diffuser. The practical application of this convergent divergent diffuser is in typical supersonic wind tunnel. In supersonic wind tunnel, which is having a schematic something like this, where a convergent divergent nozzle is placed first upstream, and there is a constant area passage something like this, and then there is a convergent divergent diffuser is attached, which is something like this. Now this constant area passage here, I am terming it test section of this supersonic wind tunnel schematic. The flow entering here first encounters this CD nozzle, and at the downstream of this test section attached with the flow encounters CD diffuser. Our objective of wind tunnel experiments in supersonic test section to make the test section shock free, because you will have a model mounted over in this test section to measure the various parameters of flow properties. Now, in doing so, since when a constant passage is attached just at the exit of a convergent divergent nozzle, then by controlling the back pressure here somewhere at the downstream side, you can move this shock further from upstream placement to somewhere here, so that the test section will become totally shock free, and hence an isentropic flow theoretically can be obtained inside the test section. However, as soon as the shock reaches at this particular point where another assembly of a convergent divergent diffuser is placed, the shock cannot stand at the convergent portion, and because it becomes unstable. So, to gain the stability, this shock suddenly moves and stands somewhere here, that is in the divergent portion of convergent divergent diffuser. In such a case, what we essentially find that if the downstream side where the shock is standing, if the stagnation pressure becomes, let us say, PO2 dash, and the Mach number here somewhere we can say M1 double dash, the upstream Mach number. In this case, again if we write down the nozzle pressure ratio, total nozzle pressure ratio, let us say lambda double dash based on something the similar condition like this, then we can again obtain 1 by lambda double dash such that PO2 double dash PO1, and then such a big expression which is a function of, again I can say, function of M1 double dash, where up M1 double dash denotes the Mach number just upstream of this shock wave in convergent divergent diffuser. What we essentially find here that PO2 dash is further increased due to placement of convergent divergent diffuser, and hence the operating pressure ratio required to run this supersonic wind tunnel of a convergent divergent diffuser test section and convergent divergent nozzle test section and convergent divergent diffuser, this total or overall operating pressure ratio further decreases, that is lambda 2 double dash will again further will be lesser than lambda dash. Another benefit here, the point here should be noted here, that since we are in this convergent divergent or supersonic wind tunnel, we encountered with two test throat sections. First is denoted by A1 asterisk, and here second is A2 asterisk. Now, you also observe from this schematics that the area at the throat, first throat of a convergent divergent nozzle, and the area at the throat a convergent divergent diffuser, then what we essentially see that A2 star is greater than A1 star. This must be followed. Why it is so? Because if you really want to move the shock somewhere here, then to have this shock swallowing, that is the swallow the shock, which is also termed as shock swallowing phenomena from upstream side to downstream side, then A2 must be larger than A1 star. This is also the case, that is PO2 by PO1 is equal to A1 star divided by A2 star. This expression is obtained using the mass flow rate, because whatever the mass is entering from upstream location must be same as mass at the downstream location. Hence, the equating the continuity equation from the continuity equation at the throat location 1, first throat, and the second throat location by nomenclature, these two, this gives you the PO2 by PO1 is equal to A1 star by A2 star, and since PA2 is less than PO1 and hence A2 star is more than A1 star, readily we can see here. Now what happens as soon as the shock wave travels downstream and stands somewhere in the divergent portion, is still the strength of the shock is much large. Now to make the, and that will be costing to your the power supply through which you are running your supersonic wind tunnel for these experiments in the test section. Now our objective is to make the strength of shock wave as small as possible, that is you are trying to convert normal shock into weaker normal shock or weaker waves. In doing this exercise, since the controlling pressure back pressure has been lowered down such that as soon as a stable normal shock appears in the divergence section, you start slightly increasing the back pressure such that the shock further travels upstream, and since the throat again here is choked, and since the Mach number here obtained as second throat is also 1, then by increasing the back pressure from this stage to further up, the shock travels further upstream, and a stage comes that at a particular back pressure this shock wave will just stand over here and becomes very weak, because this is a sonic condition state, because throat is choked and Mach number upstream is 1. Therefore the waves become almost having negligible strength, and you essentially theoretically finds the whole supersonic wind tunnel is clearly up isentropic, which is desired. And in this idealized condition, when this happens, that the shock wave just standing at the second throat exit to have a negligible strength, in this condition theoretically A1 star will become equal to A2 star, but in practical scenario this never happens. Always A2 star is more than A1 star, is deliberately manufactured or constructed in such a way the shock does not come directly at the throat but slightly away from the throat in the downstream side. This is due to, because the shock as soon as it becomes unstable, when it is directly at the throat, then slight affecting due to some perturbation or some external causes, this shock waves can move or further travel upstream. To avoid this, shock is usually kept slightly downstream of the throat, but since it is near to the throat, its strength is still very small, and hence the power supply will not having much trouble in doing so, or it will be cost effective. Now while deriving the static pressure ratio P2 by P1, we have defined a parameter, strength of the shock. A strength of the shock is defined as P2 minus P1 upon P1, and since we know about the shock static pressure ratio across a shock wave, if you introduce that here, then we will find the strength of the shock wave here denoted by capital P. We have obtained 2 gamma upon gamma plus 1 m1 square minus 1, because P2 by P1 is equal to 1 plus 2 gamma upon gamma plus 1 into m1 square minus 1, and this one we have taken left hand side, and hence what we essentially see, gamma is a constant for a particular gas such that air in our case, the strength of the shock is directly proportional to m1 square minus 1, that is the Mach number. That is, higher the Mach number, stronger the wave is. Now in such an exercise where strength of shock is denoted by P, capital P, we can write down rho 2 by rho 1 from Rankine-Hugueniot relationship in terms of rho 2 by rho 1 and P2 by P1. We can obtain this equation, that means using the Rankine-Hugueniot RH relationship such that rho 2 by rho 1 can be obtained as a function of P2 by P1. And since P2 minus P1 by P1 is written as capital P or strength of the shock, using this we can get this expression. And now entropy change can also be written something like delta S by Cv ln P2 by P1 minus 1 plus 1, that is slight algebraic manipulation. That means what essentially we are trying to have, that how does the strength of the shock is governing the entropy change across the shock wave. In doing this exercise, if we obtain like this, then this expression is something like ln 1 plus x, where x is a variable. Using or expanding this expression as a logarithmic series, because this is essentially nothing but ln P2 by P1, but I am interested in having a capital P which is nothing but our strength of the shock, and in doing so this becomes 1 plus P2 minus P1 by P minus 1. And if you open in terms of P here, that is this fellow becomes P2 by P1 minus 1 becomes P, and hence delta S by Cv is equal to ln 1 plus capital P and minus gamma ln rho 2 by rho 1. Now expanding this, we will obtain the expression something like this: delta S by Cv ln 1 plus P minus gamma ln 1 plus gamma plus 1 by 2 gamma P, and plus gamma ln 1 plus gamma minus 1 by 2 gamma into P, something like this. Using the expansion, logarithmic expansion, which is nothing but epsilon minus epsilon square by 2, epsilon by cube by 3 minus epsilon by 4, where epsilon is a parameter which is much less than 1. Introducing the strength of the wave of this in terms of this expanding by keeping replacing the P with 2 gamma upon gamma plus 1 m1 square minus 1, you will obtain the series by solving something like this. Now if m1 minus 1 or m1 is very small, then we can definitely ignore these higher order terms. Thus in this condition, when considering only one term, such that for low or moderate Mach number, then delta S by Cv can be written as 2 by 3, again a constant, gamma upon gamma plus 1 square, again a constant, and m1 square minus 1 to the power cube. That means if this is a constant, then delta S by Cv can be directly written as directly proportional to m1 square minus 1 to the power cube. What we essentially find it that the entropy change across a shock wave is proportional to the cubic of shock strength. That means for a given Mach number, that is for a given strength, the cube of that this is proportional to the entropy change. That is, the entropy change across the normal shock wave is directly proportional to the strength of the shock to the cube. That means if you are really interested in decreasing the entropy or amount of disorder inside a flow, you must decrease the shock strength as much as possible, and that can be only obtained by when m1 is very small. But however, when m1 is not small, but still the amount of disorder must be decreased. In doing that exercise, we have some other tools available. That is, one popular tool is geometrical modifications. see here the first case here that if the sudden change in the slope occurs of a surface, that means the flow upstream is turning into itself. We have seen that an oblique shock wave forms something like this, where if this wave is standing from upstream direction to an angle of beta, which is called wave angle, and theta a, that is the wave angle. When the flow turns into itself, an oblique shock or compression waves are formed, and this kind of corners where this happens is termed as concave corner. Whereas when the surface moves something like this, that is the below than the upstream direction, and that is a convex, when the flow encountered with a convex corner, then the upstream Mach number, as soon as this encountered with a sudden change in the surface inclination in the downstream side, such that the flow away from itself, move away from itself, then an expansion fan you can see from at the vertex to expanding in these directions are formed. That is the property of expansion fan, that it relaxes the flow, that is static properties relaxes, however the Mach number increases, whereas in the counterpart, oblique shock counterparts or shock wave counterpart, the flow property jumps, whereas the Mach number decreases. So shock and expansion fans are two opposite phenomena which takes place in the supersonic flows. Now let us deal with this oblique shock wave. So far P2 by P1, T2 by T1 or rho 2 by rho 1, all these static thermodynamic property ratio we have evolved with. Assuming this normal shock is perpendicular to the upstream direction. However, we have also seen and that all these normal shocks are generated inside the internal flows, that is nozzle, diffusers or any duct. But in the naturally occurring case where internal flows are not present, whereas in the external flows are present, then these normal shocks do not occur, and the oblique shock forms. That means these kind of oblique shocks which are encountered here, our objective is to have the upstream and downstream property ratio, that is P2 by P1, T2 by T1, rho 2 by rho 1, stagnation pressure ratio PO2 by PO1, and what about delta S in the case we are interested in calculating these changes. In doing this exercise, we first assume, let us say, if the velocity rather than the Mach number, let us first investigate or analyze this situation in terms of velocity. Now if let us say velocity v1 is approaching an oblique shock which is standing by making an angle beta from the upstream direction. Now resolving this velocity into two parts, that is parallel to the wave and perpendicular to the wave, and likewise the velocity which is coming out of the shock wave flow velocity, if this is v2, parallel to that vy2 and perpendicular to vx2. Now according to the continuity equation, since there is no flow parallel to the shock wave, hence the velocity component vy1 and vy2 remains unchanged. Therefore the only change which is experienced is in the normal component of the velocity across the oblique shock wave, that is vx1. The actual vx1 you can see schematically as well, that the magnitude of vx1 is decreases to vx2, that is a smaller magnitude, and since v1 or v2 is nothing but square root of vx square 1 plus Vy1 square. And since Vx1 reduces while the Vy1 is remaining unchanged, hence V1 and V2 are basically changing because of Vx1 and Vx2 alone. Now, if you divide this Vx1 and Vx2 by speed of sound, you can obtain the m, let us say x1 upstream side and m Mach number x2 downstream side. Now, our objective is to relate these velocities, the normal component of velocity Vx and Vx2 in terms of V1, so that we can obtain the normal component of Mach number and the upstream and downstream with these angles. Now, since the flow will be always parallel to the surface, if the surface is turning into itself, that is the flow is encountered a convex corner, a concave corner where these oblique shocks are generated like the previous case, then in this case if theta is the wave angle, beta is the wave angle, and m1 and m2 are upstream and downstream Mach number, then in doing this exercise and resolving these components likewise, we can get the component of normal component in terms of m1 sin beta, because this is nothing but Vx1 is equal to V1 times sin beta. From trigonometry we can resolve. Similarly, the downstream side and upstream side, that is the downstream side here, the m and 2 using this trigonometry relationship and using the downstream Mach number can be related as beta minus theta from the trigonometry, and then we can find m1 and mn1 and mn2 from the m1 and m2 using the wave angle and the wave angle. Now, since we have here got a very important relationship that mn1 is equal to m1 sin beta, then wherever we have developed the expression for a normal shock wave P2 by P1 or T2 by T1 or rho 2 by rho 1 and PO2 by PO1, if we replace m1 with mn1, then we will readily available with the oblique shock relationship. That is what exactly has done in this slide, that is P2 by P1 1 plus 2 gamma upon gamma plus 1, and since in the normal shock relationship this was m1, we have replaced m1 square sin square beta minus 1, and likewise in other expression. Then we can see if we have developed the expression for normal shock wave by just replacing m1 with m1 sin beta, we can obtain these relationship static pressure ratios across the oblique shock wave. And furthermore, since we have seen that the downstream normal component can be obtained in terms of mn2 upon sin beta minus theta, and since mn2 is again we can obtain using the mn1, that is the from the normal shock component upstream, then mn2 and mn1, that is essentially this is mn1, can be related by this expression. Hence, once mn2 is obtained, you can also obtain the m2 at the downstream side, and using all these expression, please note these the gas tables are formed, and hence the students must be encouraged to use that gas tables which tabulates the static pressure ratio, temperature ratio, density ratio, stagnation pressure ratio and the Mach numbers, rather than using these complex relationships. However, the final point, one more thing which we see here, that since we have resolved the oblique shock and derived this expression using the mn1, what we essentially can say, the mn1 must also separately should be greater than 1, and hence since m1 can be written as m1 sin beta, hence the m1 sin beta should also be greater than 1. And therefore, since the tangential component of the Mach number, whether mt1 tangential upstream of a oblique shock wave and mt2 remains unchanged, hence what we essentially find that in a oblique shock wave it is not necessary that the downstream side, the Mach number, is always subsonic, unlike normal shock waves. And then whenever the oblique shock not necessarily subsonic, where it decreases in comparison to m1 but still supersonic, we call this kind of oblique shock waves weak. However, once due to mn2 and mt2, if m2 also becomes lesser than 1, then we call the oblique shock form as strong. Thank you very much.